Yep, you can start.
Okay, thank you everyone for joining. Today is going to be recitation 5. We're going to talk about the face verification, which correspond to the homework 2 part 2. And oops. First of all, I want to say that there's a homework 2 bootcamp YouTube video recording on the course website. Make sure you watch it before you get started on homework 2 part 1 or part 2. It's going to be really helpful. It answers some most popular questions that you may run into in the future. And this is the agenda. Firstly, I'm going to talk about the problem statement of face verification, and then sorry. And then I'm going to talk about the model architectures, and then the metrics during training and inference. And finally, there will be a code demo. So first of all, the problem statement. So the face verification is a very simple task. Given a pair of face images, what you need to do is to determine if they are of the same person or not. So for each face image, you need to firstly use a CNN to extract these features, or we can call it like embeddings in the write-up. And the second step is to compute a similarity score between the two feature vectors. So very, very simple, only 2 steps. And here is a graph that shows the pipeline of a face verification system. Basically, 2 images goes into a CNN model, gets the feature, and then compute the similarity metric. And here are the questions you may have. So for the first step, we are talking about a CNN. So very naturally, what is the what is the architecture of this CNN? And of course, how do we train this model? What is the loss function? And for the second step, we have to compute a similarity score. And the question would be, what is the metric of the similarity score? And we will address these 3 questions here one by one. Okay, first of all, the model architectures. The architecture of the CNN model is entirely free, up to you. You can pick any model you like. I'm going to briefly go through the evolution of CNNs for visual tasks, mainly through the years, and do some simple recommendations. It's up to you what you're going to choose. So the first model I'm going to introduce is the AlexNet. It is the most ancient one, I guess. It is published in 2012 and was the winner of the ImageNet that year. The features about this is that it uses the ReLU and implements dropout instead of batch norm between layers. It also requires data augmentation methods to achieve a good performance. And the network is trained using SGD with momentum. However, compared with the following networks, which uses the atom a lot more often. Okay, the second architecture is VGG. It was introduced in 2014, and as shown in the graph, you can see the feature is that it reduces the size of each layer, and yet increases the overall depth, which is the channel-wise. The idea is that the CNN must be deep in order to work well with visual data. So this graph is an illustration of VGG16. All the convolution kernels are 3 by 3, and the max pooling layer is 2 by 2. VGGNet is, I think it is the first widely used convolutional network for visual tasks. So it is very, very good at dealing with images. Even now, it is still widely used. So you can see it in almost most of the papers. And the third one is going to be Resnet. It was introduced in 2015. It utilizes the bottleneck architecture efficiently, and it learns them as residual functions. So the highlight here is the residual block. So the idea is illustrated in the graph. So you can see the X here. It skips the weight layer, two weight layers and one value, and then directly adds to the output of that two layers. So the outcome is that it is easier to optimize this to this network because the loss function can be can go backward more efficiently, even when the network is very, very deep. And the accuracy of this Resnet in 2015 was uncomparable. It was the highest. And even in today, it is the most widely used backbone network for visual tasks. So for you to get started, I would really recommend VGG and Resnet. For Resnet, I would recommend you to try Resnet 18 or Resnet 50. Resnet 50 is a bit larger. You may want to use, you may want to decrease your batch size if your GPU cannot hold that much memory. You may want to start with Resnet 18. I think you can, if you are able to train a good Resnet 18, you should be able to have a very good performance in this homework. And these are relatively newer models. This is Densenet. It is introduced in 2016, and I think it was the best paper in CVPR that year. It includes a stack of dense blocks followed by a transition layer. So you can see in the graph, it illustrates the idea. Okay, so it strengthens feature propagation, encourage feature reuse, and decrease the number of parameters. Yes, I think it was designed mostly for image classification. And yeah, feel free to try it. And the next milestone, I would say it's Mobilenet in 2017. Mobilenet has two versions, V1 and V2, and both of them are very, very important because they have something very unique. So in V1, it introduces the depth-wise separable convolution. So this convolution has much fewer parameters, and it is designed for mobile devices. And V2 introduces the inverted residual block. I'm not going to introduce the very detail of these two. Feel free to dig into those things if you would like to. And Mobilenet, yes, you can try them. They are very, very efficient network, but if you are not confident with your parameter tuning methods, I would recommend you still start with Resnet or VGG because if a network has much fewer parameters, it might be an indication that this network might be a little bit harder to train. Okay, here I want to say something more about the model. Let's go back to like the VGG or the Resnet. So make sure you remember the resolution of the input image for homework 2 part 2 is 64 by 64. However, the original Resnet, no matter if it is Resnet 18 or 50, the resolution of original input image is designed to be 224 by 224, which is almost 4 times bigger than our input. So this means that you can, ideally, you should not directly use the original Resnet 18. Because I remember the first convolution kernel in Resnet is 7 by 7. So imagine doing convolutions on 224 by 224 images using a 7 by 7 kernel is okay, but on a 64 by 64 image, it is not okay anymore. So you want to fix this problem. So basically you have two choices. The first choice is to modify the kernel size yourself. But this step, you may want to fix the size of every layer. So you may not only want to like reduce the first kernel 7 by 7 to 3 by 3. That's not okay. You have to fix every layer to make sure the size of each feature map can be accepted by the network. And the second choice is that the second choice is much easier. I think you can try that first, because all you need to do is to resize your 64 by 64 image back into 224 by 224, and then feed the resized image into the backbone network. That's much easier, and I think it should work. Okay, that's the model architecture. And the second question is, how do you train the model? So in the write-up, if you haven't read it through, so in the write-up, it introduces two methods. The first method is to train the model with classification task, and the second is metric learning. So here in the recitation, I'm going to encourage you to start with the classification method, because it is much more straightforward and easier. But for some of you who may have experience in metric learning, I would also recommend you to try that. It is the most interesting part of this homework. And for classification network, it is very natural that the loss you will be using is still cross entropy loss. It is the same as homework 1 part 2. And there are other losses in the write-up, and for sure you can try those losses as well. But I think cross entropy loss alone can give you a good performance. So let's revisit our pipeline overview. So here during training, after the images are fed into the CNN model, you are going to do a classification task. In the training data set, I think you're given 3,000 or 4,000 different people's faces, and that's how many classes you want to classify. So you are going to use a cross entropy loss to train the CNN model. And during inference, you're not going to use the cross entropy loss anymore. You're going to use the feature vector directly. So you directly ask your CNN model to directly return the feature vector instead of giving you a single loss. Okay. So the last question we're going to talk about is given two feature vectors, how do we compute the similarity score? In the write-up, we introduces the cosine similarity, and actually this is basically all you need. So it's really simple. So I give you two links here. The first one points you to the wiki of cosine similarity. And the second one is the PyTorch implementation of cosine similarity. So you don't even have to implement it yourself. All you need to do is to call this API, really simple. And here are two questions I want you to think about for yourself. The first one is how does cosine similarity compare to L2 similarity, or why we are not recommending L2 similarity in the first place. And the second question is, in other applications, we compare the similarity score against the threshold to make a binary decision. So here the cosine similarity is going to give you a continuous number between 0 and 1. And you may want to compare it against a threshold, for example, 0.5. If the number is bigger than 0.5, that means that you can make a decision that the two images are of the same person and vice versa. So, however, in homework 2 part 2's Kaggle submission, what would be your submission be like? Is it going to be the similarity score itself, or you have to compare it against the threshold? So that's a very important question. You have to be very clear before you make any submission. Okay. And revisit our pipeline again. So here the metric is going to be cosine similarity and outputs a similarity score. So yeah, I think this is much simpler, this task. Okay, that's my part. I think I can answer a few questions if you have any about what I have talked so far. It seems that I have to stop sharing my screen to see the chat. Any more questions? Do we have to use the feature map cosine similarity, or is it just a recommendation? Well, if you have any other ideas, you can talk to us. Yes, but we strongly recommend you to follow the feature map and then cosine similarity. This roadmap, because not only because this is the standard way of doing face verification, but also that we are familiar with it, so we can help you with any question you have. So we train with cross entropy laws, but use similarity to evaluation. Yes, correct. If we use Resnet architecture, what other parameters would we tune? Okay. Yeah, very basic stuff. The learning rate, the weight decay, and also the strategy you want to adjust your learning rate. For example, like after 10 or 20 epochs, you want to decrease your learning rate by a certain number. You may another thing is that you may not want to tune your Resnet. So if you are not sure about if your Resnet looks correct, you can ask on Piazza or go to the office hour. We don't recommend you to do something like network architecture search manually. That is really inefficient. yeah, if you are not sure about how's your architecture, you can just ask us about it. Or more simpler, you can use like VGG, which I don't think it requires any modification. Okay, I think that's all the questions. So I'm going to hand over the recitation to the coding part.
Yep. So let me share my screen. Can you, yeah. You can see my screen, right? Jisoo, can you confirm?
Yes.
Yes, yes.
Yeah.
Okay, yeah. So welcome everyone. Let's talk about the code. So of course, this is not a code for the homework itself. This is just a demo code to give you some idea on CNNs, how to use them. And this is the agenda of this code discussion. So first I'll briefly discuss how to make your own custom dataset and data loader. And then I'll tell you the recommended approach, which is to just use image folder from Torch Vision. And then I'll talk about how to implement a basic residual block and how to incorporate that in a CNN model architecture. And finally, I'll just give you some code on center loss and triplet loss, which I won't explain. I'll leave that to you. So yeah, let's get started. So first of all, let me tell you the problem statement. The problem statement is similar to homework 2 part 2. And this is what the folder structure looks like. You have a folder called medium, which has 5 different labels. And in each label folder, you have a bunch of images. So like you can see, there's nothing special in here. It's just a bunch of images. If you open, maybe, yeah, some girl's image pops up. So like I said, nothing special here, just a bunch of images in a bunch of folders. And that's it. That's our data. So of course, we'll start with some imports. And like I said, first I'll tell you how to write a custom data set with Dataloader. So the key to this is to write your own parse data function, which we have provided for you, which will basically take the name of the folder and return to you the list of names of all the images and the label list. So you don't have to worry about this. And the number of classes, of course, which is 5. So you just pass the folder and it will basically walk through the folder structure recursively and fetch all the image names for you. So once you're done with this, you have all the image names, then you define your data set. And data set is also simple. You just initialize it with the file list, which is your file names and your number of classes. And in the get item, basically, when the data loader will ask dataset, okay, I need the first 50 images. So it will call this get item function multiple times and say that, okay, give me whatever data you want me to give for index 0 or index 1. So once you have that index, you will simply open that file name and convert it to a tensor using the Torch Vision's inbuilt toTensor function and get the corresponding label and just return both of them. So the purpose of showing this custom data loader is, again, if you want to use it this way, maybe like in verification task, you want to load the 2 images and that's how you want to return it. So that's up to you. That's how I did it last semester in this course, but there's a better way I'll show you. And let's see. So yeah, that was your data set. And once you instantiate your data set, then you can have a data loader, which will just use that data set. You can specify a batch size like homework 1, like you did it homework 1, shuffle it, number of workers, all that. And yeah, that's your data loader. And then you can use it later for training. Now that was the first way. The second way is super simple. Just give the folder name and PyTorch will take care of it for you. So yeah, that's the recommended way. And in case you're wondering how will I deal with the two images, because since you need to deal with pairs, right? Ultimately, you need to output, you need to calculate the cosine similarity and see if they belong to the same person or not. So one advice I can give there is you can simply just iterate through all the images, get their embeddings, and that you can do simply just by loading this folder, and you can store those embeddings in an array, and then you can run your program on top of that to calculate the cosine similarities pairwise. So that way you don't have to worry about loading two images in through your dataset like I did. So yeah, that's the second way. Just provide the folder name, get the dataset, and just feed it into the data loader. So as you can see in this example, the total number of images are 1889. Now total number of images in what? Total number of images in 1 plus 2 plus 3 plus 4 plus 5. That count is 1889. And there are 5 classes. Okay. Now let's talk about, now our data is loaded. Our data loader is ready. We can iterate through it anytime. Now we'll talk about the architecture. So let's talk about residual block. So as you explained, so I wouldn't recommend to just use Resnet. Like, although Resnet is a good architecture, but you're welcome to use it, and maybe it is the recommended way. But just because we are mentioning it in the code of this recitation doesn't bound you to only use this and nothing else. Like I said, this entire code is just a demo example, and consider it separate from part 2. Anyways, so this is your residual block, and like Yizu said, the basic idea is that you pass your input through a bunch of convolution layers and batch norm layers, and you have a separate shortcut 2D convolution layer, and you will feed the input directly to that layer, and then you will just basically add the output of that to the output that you got from passing the original data through the previous layers. So instead of passing the output of the previous layers as the input to the shortcut layer, you pass the input data itself to the shortcut layer. And then you add that output to whatever output you got from the previous layers. And then you apply the activation function, and then you return the output. So that's a basic block. So just think of it like, okay, now that I've thought about this, this is once I create an object of basic block, I don't need to worry about what's in it. I'll just call forward function, it will take care of it. So this basic block will ultimately be plugged into a bigger architecture, which I'll show you now. So let's see. This is our network class, and to initialize it, basically just have a hidden sizes vector. So before I explain this to you, let me give you a small example so that you guys can understand it better. So ultimately, when this is the network class that I'm trying to build, and when I'll call this, I'll provide it some parameters. One is number of features. The first is number of features, which is your number of input channels. Yeah. And then hidden sizes is however many hidden sizes you want to provide. In this example, only 32 and 64 are used. And then number of classes, which is 5 in our case. And then you try to initialize the weights of this network through one of some initializations. Could be Kaiming, could be Xavier. In this example, I think, yeah, we used Xavier. Let me show you that init weight function quickly. Where is the init weight function? Yeah. So yeah, we use Xavier normal initialization whenever the type of M is contour or linear. Yeah. Anyways, so now you know what the input of network is. Now let's jump into the network class itself. So yeah, like I said, you have an array of hidden sizes. Number of features is the first element of the array, which is your input channels in the first layer. And then you have hidden sizes and number of classes. Then you just initialize empty list of layers, and then you start appending these building blocks into that. So each element of this list will comprise of 3 things. The first one is a 2D layer. where the number input channel will be hidden sizes of IDX. Basically, in the first layer, this hidden sizes of 0 will be your input channel number of features, which in our case will be 3. And out channels will be uh, the next, the value corresponding to the next index in the hidden sizes array, which will be 32 in our case. And then you apply ReLU on top of it. And then herein lies your basic block that we discussed in the previous section. So this is how you just keep on adding multiple entries to this array. And of course, that's not enough. You need to make sure that the parameters of the constituent parameters of this list are actually absorbed by the parent class. So that's why you use sequential. You merge them together. Otherwise, it's just an array, right? And your gradients won't work. When you try to do autograd, it won't work because it won't know that there is an nn dot module objects within this layer. It's just a list. Anyways, so then you have a linear label, which is simply a linear layer. I'll tell you why it's called label, because this is the layer we'll use mostly. And since I also spoke about using center loss, we'll have another linear layer. So both are similar to each other. The first linear layer is used for classification, and its input is self.hidden sizes -2. So what is -2? Go to the last element, go to the second last element of hidden sizes. So you take that and then you output the number of classes. So yeah, which is 5. So this is used for classification, this linear layer. The other linear layer is used just to get the embedding. And by embedding, I mean another, like just a bunch of values, right? Just a bunch of float values whose size is feed dim. Feed dim is what? Feed dim is 10. So basically you'll get a 10-dimensional vector if you pass the output of these layers through this linear layer instead of this linear layer. So which will act as an embedding, which you can use to calculate cosine similarity. Okay. Now all we have done is just initialize a bunch of things. Now we actually need to use them, right? Otherwise, what's the point? So we'll go in forward, and this is our input. We'll apply our layers. We don't need to worry. PyTorch will take care of it. And after that, we do average pooling on the third and fourth dimension. So I think, yeah, the average pooling concept is covered in class. Basically, this output will be a 4-dimensional vector. Let's call it X, Y. Let's call it A, comma, B, comma, C, comma, D, the shape of this output. So basically you're specifying C and D shape. Let's say the shape of C and D, in this case, it will be 7, the value of C and D. So you want to remove this dimension. Why do you want to remove it? Because in the next layer, you want to pass it through a linear layer. And this is how it works, right? You want to make sure, this is why you provide these output channels in the 2D layer, because ultimately that's the number of channels you'll get. And in many cases, that's why you do pooling, so that you can remove the rest of the dimensions and lower the number of parameters as well. But yeah, like if the size of this is output channels cross 7 cross 7, right? So that 7 cross 7 will be removed after this 2D pooling is done. And then you reshape it. And like I explained, you will pass it through the linear layer, and you will pass it through the linear C-loss layer as well. And you'll return both in the forward function. So if you're not using C-loss, you only need to use the classification linear layer for now. And yeah, that's about it. And this is your init weights function that I already told you. This is your simple train function, which is similar to homework 1, nothing special here. You just say, okay, model.train, then you start the epochs, then you have your average loss, then you start enumerating through the data loader, and you send it to torch. And yeah, I guess this is pretty straightforward. I don't need to cover this. So yeah, you just call your model and then get the loss and just call backward and optimize. Optimizer dot step is just you take a step in that direction. Now, where have I initialized this? I'll show you in a second with C loss. And yeah, you get the average loss. Yeah, it's pretty straightforward stuff. You just train it, then there's a function for classify, there's a function for verify. You can look into this on your own. One thing I would suggest is, if you decide to use portions of this code, make sure you understand every line of it. Like I said before, don't just copy paste it. Don't assume that this is a code given for homework 2 P2, because it's not, and you'll fall into trouble. Okay, so yeah, you just load your dataset data loaders. I think I've covered everything. Bunch of parameters, hyperparameters, and this is your optimizer. In this example, we're using STD with some learning rate, weight, decay, momentum, and then you train the hell out of it. Okay, and then you have your center loss, which I'm gonna leave to you. So this is a GitHub copy pasted code of center loss initialization and the class definition, which you guys are welcome to use as well. You don't need to reference it, I guess, because we are providing it to you, and or you can implement it from scratch as well. So I'll just give you one hint here. Basically, remember our forward function was returning two outputs. So we'll use one of the outputs for the normal label loss and the other output for the center loss. And what is center loss? Center loss is basically like you want to make sure that for each of the classes, your features, the model tries to learn a center for the deep features in each of the classes. And this loss function basically tries to penalize the distance between the deep features and the learned centers in each of the classes. So I've included a link to the GitHub repo here, which also has a paper link, I believe. Yep. So you're welcome to read this on your own and study what center loss is. Okay. Where were we? Yeah. So we get our two losses, we sum them up. We have a weight parameter which says how much we want to weigh the center loss. And we can just, in this example, it's just set to 1. You can experiment, think of it like a hyperparameter experiment with different values. And then just call loss.backward. And as always, PyTorch will take care of it for you. And then you call the step function. Now you see here, there are two different optimizers, which is how it's supposed to be. You know, I said I won't go into much detail, but I am going into much detail. So this is your criterion variables. One is for the cross entropy loss, other is for center loss. This is the class we just took from GitHub, the definition of center loss. And then you have two different optimizers, both STD, that you will step separately, but simultaneously. By separately, I mean in separate lines, but simultaneously, like in the same iteration. And then you just call loss.backward, and that's how you train it. And yeah, this is an example of that training. And then there's also triplet loss, and I'll keep my promise this time and I won't say anything about this. So it's just an example for you. So yeah, that's it from my side. If you guys have any questions, please let me know. Let me see the chat window.
Hi. So there's so I see that your code for the Resnet blocks, it looks pretty similar to like the example one given on the PyTorch website. Are we allowed to use like any like if we want to pull from that directly, is that okay at all?
No, that's not allowed at all.
Okay. Okay.
You have to implement it from scratch. That's like one of the main goals of this homework. Yeah.
Okay, but taking from this notebook is fine?
Yeah, taking from this notebook is fine. Yeah.
Okay, cool.
But that's a good question. Thank you for asking. Yep.
The data loader, I saw that the worksheet recommended using a Torch Vision pre-designed dataset class.
Yes.
You created your, so wait, I'm a bit confused. So is this the data loader or the class to load? You have two data.
Yeah.
Can you explain?
Yeah, sure. Let me clarify, and sorry for the confusion. So basically, you can ignore all the code between this parse data, even starting from this entire section of custom dataset with data loader, you can ignore. I would say the recommended way is to simply use these two lines. So how does it work? First, you need to define a data set. What is the job of data set? Whenever data loader will say, okay, get me the data for index 0, data set will provide the data. Now, one option is to make your own data set, which is given here. I wanted to provide this code so that if some of you want to have more control, customize it, return two images at the same time, which is how I did it, you have some reference for it. That's the whole reason I provided this code, but you can completely ignore this. And like I said, so there are two options for dataset. First option is use this image dataset. And second option is use this inbuilt function. Now, if you want to use this dataset, you need to provide it with some data, right? What is the data? File names, which is why you need this parse data function. So if you decide to go with option 2, which is given in this section, you can completely ignore the parse data function and this image dataset class.
But you couldn't use the second one for the metric learning because this data set only outputs one image.
Yeah. So
or is it possible, could you create, I don't know. Okay, so use a custom one if you're doing metric learning.
Yeah, exactly. So metric learning is not a mandatory thing to do. If you decide to do it, well and good. So yeah, it would help you there. Like I said, if you want to return two images, you can have more control. But if you implement your solution without metric learning, then maybe you don't need this. So that's why we wanted to provide both the options. It's up to you. You can experiment with whatever you like.
I have a question about the Torch Vision data set and data loader.
Okay.
And this pertains mostly to the Kaggle and how that's set up. For the output, we need to put the file pair that was compared and the output score or something. I need to double check what the exact output is.
Yeah, I think it's 0 or 1, 0 for if they don't match and 1 for if they match. Yeah.
Okay, cool. So will this data loader or data set give us those file names, or do we have to find a way to loop through them ourselves?
That's a good question. You'll have to find a way to look through it yourself. So the purpose of this data loader is you do your training and then maybe you store your embeddings for each of the images, and then you can have more data structures in Python, right? Maybe just make a map of this mapping from file names or the image IDs, however you want to store it. And the value can be the embedding itself. And then you can run your NC2 combinations over that stored value. So that is what I was trying to say before as well. You can just use this and not have your code return two images or something, your pairs or something. So just deal with one image at deal with only one image at a time, and then just write simple Python code to iterate over it. But that's just one design option. There could be many. Like, yeah, you can just use. Yeah. I won't say anymore. Yeah.
Okay, so it's for us to figure out.
Yep. But always you're welcome to post any questions, any confusions on Piazza or come to officers. So don't get stuck on this for too long, because I guess, teaching very good Python is not the goal of this course, I would say. So yeah, don't worry too much about it.
And question about the Kaggle, and I don't know if I'll just ask it here and I'll have to reiterate it on the Piazza. Does the order of the CSV file matter, or the order of the rows?
I would say yes. Okay. Yep. Jizu, are you still there? Can you confirm that for me? I am 99.9% sure.
Oh, which question it is?
The order of that matters, right? The order of the output. Of course, it like the test file that's given, we need whatever they submit on Kaggle, the order of the rows need to be same, right?
Yes, correct.
Cool. Okay. Any other questions?
I think someone asked if using the cosine embedding loss from PyTorch is fine.
Cosine embedding loss from?
From PyTorch.
I would let Yizu take that one. Yizu, you know the answer to that one?
Cosine embedding loss. Okay, I'll take a look about it. I don't know if it can be directly applicable to our problem. I'm not sure.
Okay. Any other questions, guys?
All right, where do we find the Jupyter notebook that you just?
We'll make sure it's uploaded on the course website. So just there's a recitations table. Just go to today's recitation. You'll find the video, slides, and the zip file, Jupyter notebook as well. Yep.
And for the first question, do we have to implement the PyTorch losses from scratch? You don't have to. So if you follow the roadmap in the write-up, all you need is the cross entropy loss and the plus some other loss you want to try. The other loss you can either implement yourself, or you can just if they are open source, you can just borrow their code. Yes.
Thanks for that. Any other questions, guys, before we conclude? Okay. I guess we're all set then. If you have any questions, feel free to post on Piazza or come to office hours. Let me stop the recording here.